Okay, so welcome everyone to our January edition of the Search Technology Meetup Berlin. Welcome at Zalando. It's quite a nice venue. I remember last time we were here, that was in 2020, also January, and then bad things happened. I'm pretty sure this time will be a better time. First of all, I want to thank Zalando for hosting us, and let's give them a short round of applause, or long round, whatever you want. Thank you. I want to make you aware that we are recording this meetup and eventually publish it, so that you know, in case you don't feel comfortable with this. Yeah, so I think I want to go to our first talk without any further ado. I'll make some community announcements further in the end. But I think while we're all fresh and no one has broken a leg while it was slippery outside, I want to introduce Samay. Samay works at Zalando, and he will speak about multimodal embeddings today and modern approaches to it. Thank you.
Yeah. Smooth start. Hello, everyone. Cool. So, hello, everyone. Thank you all for coming. Today, I'm going to be talking about multimodal embedding search with modern VLMs. There is a link to Slido. So if you want to bring out your phones, scan that QR code, you can type out your questions as the talk goes on. And yeah, in this presentation, I'll be talking about a search relevance model, which means a model that maps from a query to an item or a document if we're being general. The purpose of this project that I'm working on is we're looking for newer alternatives to our current open clip-based model. The project is a work in progress. Of course, I hope that there still will be information worth sharing to everyone over here. But on the other side, if you have ideas or approaches that I should consider for this project, I am happy to hear that as well. I'm going to introduce some modern VLMs. We're going to talk about adapting instruct-tuned models to embedding models. We're also going to talk about how to implement this using a two-tower architecture. And with the two-tower architecture, how to use contrastive loss and how to shape your training data. And finally, some inference optimizations that you would use in order to deploy this to production. Cool. So this is my take at doing the meme template without getting into sort of like licensing issues. I don't know if that's a thing. So CLIP is a model, or the paper was published in February of 2021. That's 5 years ago, if you can believe. And it was a pretty good idea at the time. You have a vision tower on the top left, and the top right, and you have a text tower. You encode images and text separately, and you pass it through this contrastive loss function. But it was really good at bringing together embedding representations of text and images. And fast forward 5 years, just in the last 3 months, we've seen some really good, impressive, small VLMs that have been released. Notably, we have Ministral 3B. Mistral AI's model names are always the toughest to pronounce. Qwen3 VL, also a 2 billion parameter model, instruct-tuned. And just like 3 weeks ago, they released an embedding model as well, which is directly applicable to what we do over here. Newer VLMs are good because in the last 5 years, the LLM space has made some progress, if y'all might have noticed. And they can do all sorts of things like OCR, recognize patterns, answer questions, so on and so forth. And this is done because, I wonder if you can see my cursor. Yes, you can. So they have a vision encoder block that comes at the input, and then the output of the vision encoder is passed into the LM head. This means that it sort of natively understands images. And yeah, that's beneficial. I'll get to that in a second. So the new VLMs, like Ministral and Qwen3, they allow multimodal inputs, and they have massive context windows of 32,000 tokens. What that means for e-commerce folks like us is that instead of encoding text and images separately like you had to with Clip, you see over here, if you have product information, you encode the images and the attributes separately. You can just put all of that into one forward pass, and you get a single vector output. You don't have to get multiple vectors, average them, however you want to combine them. What's better is you don't have to worry about the difference between image to text query performance or text to image query performance versus text to text query performance, because everything's going through the same model or in one pass. So on the right, there's this paper from Gina Embeddings V4. They captured this really well. It's really small, but I'll do my best to explain it. On the top, you can see text-to-image performance is the blue distribution, and text-to-text performance is the pink distribution. So with clip-style models, there's a difference in these two different modalities. But when you have a VLM-based embedding model, this modality gap is closed and the text-to-image performance improves considerably. So this is a motivation for looking into these newer VLMs. Great, so we're excited about these new VLMs. Let's sanity check them to see if the performance matches what we want it to. So one way to do it is we take this product. It has 6 images. And you can pass in, here's a little bit in the weeds description of the kind of data that you pass into these models. You can pass in a list of images. Here they are base 64 encoded. And then there's also a giant JSON blob that I've truncated over here that describes the article's attributes. And at the end, I've given an instruction to provide summaries of each image. And you can see from the output of this model that even a small 2 billion parameter VLM is able to accurately describe the images in this picture. You can see here it's a single black athletic sneaker in a side profile, a pair of black sneakers displayed side by side, a top-down perspective. It can pick up on things like texture, rubber. It can identify parts of what you're looking at. So this stuff is really impressive to me. And yeah, it's like, okay, let's see how we can incorporate this into our production search stack. But there is a caveat, right? These models are impressive, but they are slow. For a 2 billion parameter model, it takes over 700 milliseconds on CPU and 100 milliseconds on GPU. This is before optimizations. Maybe you can chisel it down, but it's still too slow. In the modern search funnel, you typically have 3 or more phases, 3 phases generally. You have query analysis, where you do things like named entity recognition. You do candidate retrieval, which is the stuff we're talking about today. And then you have re-ranking, where you maybe use cross-encoders of some sort. And maybe you do personalization and things like that. But since we're just in the candidate retrieval phase, we just want to grab all the relevant items for a given query. And we don't want that phase to take too long. So the way we get around that limitation is through the 2-tower architecture. This addresses latency issues because each of the towers can run independently. So in a 2-tower architecture, you have a heavier item tower that you can run in batch once for all your products. And you have a query tower that's a much lighter model that you can deploy into production for your queries, because your queries will change, they'll be dynamic, you can't run them in batch. So it's a good compromise. And we're still using an artifact from the clip architecture, which is the clip loss. That helps you build these 2-tower types of models. The constraint, however, in these types of models is that the output dimensions must be the same. And during training, yeah, that's the constraint. And then during training, representations of related queries and items are pulled together. And ones that aren't related are pulled apart. I'll get to that in a second. Another good thing about the two-tower architecture is that fine-tuning the towers can be done independently as well. So let's say you have some sort of model drift. Your model's been in production for a couple of months and performance is starting to go down. In this case, you can fine-tune just your query tower, which is the smaller model, maybe account for whatever new user behavior. And if you fine-tune your query tower, it means your item tower stays the same, which means you don't need to re-index or re-embed your catalog, which means you don't have to maintain multiple versions of your item embeddings. It's just the query tower that can run and change in production, and that is convenient for several reasons. I was thinking maybe I'll pause for questions if there are any. Oh, yeah.
Thank you for the insightful talk. I wanted to ask, so why specifically the design of your architecture seemingly focused on using these large models to generate text descriptions of the image, not for example by directly generating some embedding from the image. So for example, so generating embeddings from text description, text queries, and the image in the same space, and then doing some similarity search in that space.
Okay, so the question is, why not just use these models to generate text and then do text-to-text search off of that? I'm just listening, yeah. Okay, yeah. Sorry, we'll get back to you for sure after. Okay, so going back, yeah. So the approach, the two-tower approach would be, we can start with the Qwen3 VL instruct 2B with an adapter. We need an adapter because the dimensions need to match. And we use a much smaller model for the text tower. So the text tower, as you can see, the query tower, sorry, outputs 1024 dimensions, and the item tower outputs 2048. So first of all, because this is an instruct-tuned model, you remove the LM head, so the final layer that does token classification, and you add an adapter that'll take the dimensions from 2048 to 1024, and it fits in this two-tower sort of setup. Also, a very helpful tip I got from a colleague is that when you are adding adapters to existing models, it's good to train just the adapter first because the model weights are initialized randomly, right? So if you backpropagate the initial couple rounds of training, you're going to be backpropagating noise and you might ruin the quality of the base model. So it's better to fine tune just the adapter first and then do a full fine tune if you like. And this is some code examples, the best I could fit into these slides on how to add an adapter. So you take your base model from Transformers, Hugging Face, and then this is the important bit where you take the base model's LM head and you set it to identity, which means it just passes through without making any changes. And then you can create an adapter. In this case, it's really simple. Like the neural nets you see on the PyTorch tutorials, a linear layer, an activation layer, a linear layer, and that's it. And then the forward pass, we do some last token pooling to get the last hidden state of the model that gives you the embedding. And then you pass it through the multi-layer perceptron that we generated over here. I'm thinking of writing a blog post and publishing this later, so you don't have to remember this. You can copy paste it later. A quick note, Qwen3 VL embed 2B was a model that was released in January, just 3 weeks ago, like I mentioned. But from the examples and the documentation, it was difficult for me to figure out how to embed multiple images and text in the same sort of block. And because the output dimensions is still 2048, we would need an adapter anyway. So it was practical to just use the instruct tuned model for this use case. But maybe this model could work for you. Maybe it could even work off the shelf without any fine tuning, without the 2-tower architecture, if you're not too sensitive for latency. I heard that if you replace your loading screens with thinking screens, people are fine with latency. That was a joke. Tough crowd. Anyway, contrastive loss. Clip loss is newer and bidirectional compared to info NCE, which is only asymmetric and is supposed to perform better. So clip loss is a good default to pick, even if you might see info NCE written somewhere in the literature. And the data format for contrastive loss is you need to have an anchor, a positive, and a negative. So for your anchor, that would be your search query. A positive would be an item that was ordered with this specific query. And negatives, easy negatives is you just, in your batch, you have random in-batch negatives. But then there's room for creativity and mining hard negatives. The quality of your negatives usually will give you good results on the quality of the model. So, for example, if someone searches for Samba 62, you wouldn't want to search for Samba, or you wouldn't show results for Samba Lux above a Samba 62. And you can see they look very similar, but people that care about sneakers maybe are a little bit more particular. Cool. So that was training. Over on the inference side, here are some benchmarks for throughput. For the item tower, where we use the vision language model, using flash attention 2 on a G5 instance, it was a little bit faster than a G6 instance. So a single GPU does about 8 items per second. And it was tricky to get torch.compile to work. But on the query tower, where we're using the smaller model, if you're using Hugging Face transformers directly without any optimizations, it takes about 30 milliseconds or about 30 queries per second. But with optimizations, we brought that down to 5 milliseconds or about 180 queries per second. So this is for one GPU. And the optimizations that we made were using torch compile, which is the new way of optimizing PyTorch models, since torch script will be deprecated soon, using the max auto-tune mode. And this is an important detail. For queries, the input shape changes, and you just have to set dynamic equals true because they try to make optimizations based on the shape of the input as well. So when you put all of that together, 5 milliseconds to get the embeddings of the query, add that on to 10 milliseconds for doing a vector retrieval. It adds up to about 15 milliseconds on average. And if you take the rule of thumb that P99 latency is about 3 to 5 times slower, you get about 60 milliseconds of P99 latency, which fits kind of well into the latency budget. Some next steps would be to try and using quantization-aware training and testing quantized models to see hopefully, they work faster than these, and hopefully they can also be deployed on CPU, saving money in production. Finally, for searching and evaluation, at this point, since we have done batch inference of all of the items, and we can do inference on the queries, we can test it out. Like I said before, this project is still in progress, so the results are still a little bit noisy. Unfortunately, not a shining demo to show off over here, but the goals are to get less noisy results and beat the current open clip based implementation, which should hopefully happen in the next couple of days or weeks. Next steps is when the model performs well, it would help with long, vague queries. So for example, if someone searches for sneakers with 3 stripes, it matches the Adidas sneakers correctly right now, which is great. But if you search for sneakers with the jumping guy logo, which is Air Jordans, that doesn't quite work. And things like this would be helpful for Zalando Assistant, shameless plug. That's our sort of RAG chatbot. You can play with it if you think it's fun or useful. And some other things that I just threw in there to try are to try SIGLIP instead of clip loss. I've read that it's good, but I haven't had any experience with it yet. And another idea is to use a VLM in the query tower as well. This would enable you to search by image. So hopefully you're not taking pictures of people on the street, but let's say you're on Instagram and you see an influencer that you like, and you like their outfit, you can take a screenshot, put it in the app, and then get a fit that matches whatever you're looking for. Sweet. And then finally, beyond search, there are some other use cases that I could think of for VLM embeddings to the extent that they might be relevant for this crowd. Actually, the first is within search, is re-ranking. If you combine the output from the item tower, query tower, and also a user tower, and put all of those into some layers of a neural net, that gives you your own personal re-ranking model. That could be useful. For other use cases, you could have a company-wide foundation or a base model for items, and you could combine it with, so an item tower combined with a query tower gives you a search model. An item tower combined with a user tower gives you recommendations, and so on and so forth. Yeah. Cool. Thank you very much for listening.
There's the first question to Samay.
Hello, thank you for the nice presentation. I do have one question related to the big tower, the item tower, basically. So how do you solve for the new products and updated products? Because I think there's always a stream of updates to the products, the description to the photo, or newly updates, but the performance of this is pretty much slower. So I think it would take time to be embedded and to be searchable, right?
Yeah, so the item tower is slower, but it's still under a second, right? So the way to solve that would be to just set up a queue, and then as soon as there are updates to your items, you can embed them as they come in. The good thing about the item tower is that it's not as sensitive to latency. So let's say a supplier makes an update to an article description, and that description gets indexed in 5 minutes. That's fine.
Any further questions? There's one.
Hi, thank you for the talk. So you mentioned that the retrieval latency was 10 milliseconds. Like, what is your vector search database like when you're retrieving from?
We use Elasticsearch, but 10 milliseconds was it was sort of an average number. It wasn't based on the dashboards. Maybe I should have looked at the dashboards.
There was a question over here somewhere.
Thank you for the amazing presentation.
Thanks.
My question is related to new users. Usually when you have new users and you don't know their preferences, you try to learn the embeddings, right? I mean, you get some signals from them that they interacted with some items. You multiply embeddings items with embeddings users, and you will get something meaningful. Now that you have embeddings from the visual model, you have the adapter, you also have the text, wouldn't be like an overkill to try to train the embeddings because you already have like models that have embeddings and you don't touch the embedding layer? How would you deal with that? Not working on the field. So for me, if I retrieve something, I don't know how it is because I'm using it with RAG, but just curious. I'm not inferring an answer, just curious.
Yeah, it's a good question. So the scope of this was to only deal with queries and items, and not quite factor in user data yet. But when it comes to personalization, I think for creating user embeddings, there would have to be an input of user data somewhere. I'm not sure how exactly it would fit into this whole situation, but yeah, there's room for creativity. Yeah.
Hi, amazing talk. Thank you very much. My question is a bit like, because in the main motivation of using these bigger models is to have somewhat more complicated queries, as you said, right? So the simple ones, even with smaller models, works already quite well, I'd say. Something like negation or the three stripes or something. Did you see when removing the LM head, whether that already removes some of the magic? Like, did you get any, I don't know how to
Yeah.
really
I
experiment
get your
with.
question. It's a good one. I assumed that in order to get a good embedding model, removing the LM head just would be the way to go. I didn't consider leaving the LM head on, but it's an experiment that I can queue up and I can report back on the results in due time. But thanks for the question. That's a good idea.
There's one more.
Thanks for the talk. I have one question regarding the training. What is fixed and what are you fine tuning? Because I understand the adapter, you basically fine tune it or you train at the beginning, right? And then do you keep the vision or the item tower fixed and only fine tune the query tower, or do you do both?
Yeah, so first it's just the adapter that gets trained and we want to keep everything else frozen so that we don't back propagate the noise. But then after that, yeah, both the towers are open for training with the exception of the vision block. Yeah. Yeah, vision block is always frozen because I looked into the paper of the VL models. The way they've trained the vision block, they went through a couple of passes. First they froze it, then they unfroze it, then they froze it again. So the outputs, the tokens that the vision encoder outputs into the LM head, they seem to be a little bit finicky, and I don't want to open that can of worms.
Hi, can you hear me? Thank you for amazing talk. I just wanted to ask, like, what was the data set size for it, and what was the labels in this case? Like, how you choose like the query pool, whether you upsample somehow, or just go with the queries you have in the application, and maybe some insights on like how much data you need for this.
Yeah, so the data is in the tens of millions. Maybe even hundreds. The way we generated the data set, so the article data set is simple. It's just the number of articles, and that's in the millions. But the data set for, I guess, the whole model, which is these contrastive query item pairs, there's an attribution query that we have that attributes queries to items that were bought. And those are the positive query item pairs. And then, yeah, the negatives, we use in-batch negatives for now. But actually, one correction, it's not just query item pairs where there was an order placed. It is items that were ordered and not returned, because that's an important bit. Returns are a big thing in e-commerce that you have to account for. Yeah. Hope that answers your question. Was there anything else?
Sorry, I can give you the mic again.
Did you need like additional manual labeling from assessors or something like this?
There's no manual labeling, but we have filters. So there's thresholds for the number of interactions between queries and items, and that helps up the quality. But already when you're dealing with orders and not clicks, because people are putting, money behind it, the quality of data is much higher.
Yeah, I have a second question. I'm curious about, is there an effect of query length on the model relevancy? So, for example, like short queries tends to be more generic, like a user search for short rather than user search for like short, blue with strides, and et cetera, et cetera. So does that, in the extreme situations of very short and very long queries, is there any thing that you notice on the relevancy of the model or the performance for inference?
Yeah, that's a good question. I have not personally looked at relevance by query length. But one thing that I will say is for shorter queries that tend to be categories like shirt, shoes, jacket, or model names like Sambas for Adidas, they get caught in the NER layer, and when there's a match, it gets forwarded over there. So for those solved queries, we can say it doesn't even hit these types of models. And I think you had a question earlier in the middle. Would you like to? Yeah.
Yeah, maybe. Yes, thank you for interesting slide. So I wanted to ask, so if I got it right, that when you was using VLMs, you was using them not to generate directly embed. Sorry, did I got it right that you was using the VLMs not to generate directly embeddings from the image, but rather first to generate the text and then embeddings out of this text? So I wonder if this was the case, and if yes, what was the motivation?
Oh, so we're not generating text from the images. We are embedding. We're putting the image. I can go back to the slide actually. This shows it really well.
Maybe I can resolve that. This was just, I think, just an example to show what Qwen could do easily these days. It was not what
Yeah.
it does. Yes.
Yeah, this was just an example for me to sanity check the capabilities of the model. But what goes into the embedding is everything on like before this instruction is what goes into the embedding model.
One more question.
Yeah.
Thanks, Samay. I have a question regarding the retrieval phase or retrieval experiment. I'm curious, what was the size of the database that you were searching in, and how did you measure the quality of the search results? Did you have some metrics for that?
Yeah, the size is in the millions. That's the amount of articles that we have. And we have a backtesting pipeline where we look at past searches and the rank or which items from those searches were purchased and not returned. And then we take the model that is currently in production and a candidate model, and we rescore the results using both of those models. And then we calculate NDCG from both of those rankings. And if the candidate model has a higher NDCG, then that's the winner.
Hi. Would you have any information, any numbers or anything about how this has affected your bounce rate, like, or your search abandonment?
Search abandonment. So in general, this has actually improved it because, yeah, I can't give you the exact numbers off the top of my head, but first we used to have, when classical search had less than a certain number of results, that's when this neural net-based search would kick in. We recently upped that threshold so that that threshold is much higher. And the direction that we want to go into is that we always query both classical and embedding search, potentially having multiple multiple indices of embedding search with different embeddings to query, because that always seems to improve all of the metrics. Because if you don't show a result, there's no way there's any conversion. I can't give you the exact numbers, but number go up.
Okay, thank you. There's one more question. I guess I get my steps in today, which is great.
Hey, really great talk, actually. I'm curious about the example that you were showing. Was it the 3 stripes one? Like, did you check maybe the gradient map? Like, is it coming from the, like how is it able to figure it out? Is it because of the image, or was it the words 3 stripes present in the text? Like, did you look into this?
Yeah, so the model that we currently have is a clip-based model, so also embeddings. It's not as shiny as the newer VLMs, but even though it's an older model, it is a good model, and it is a very well-tuned model. So it sets a high bar to beat. The way the current clip model is trained is that we take select text attributes and we take images. We have to encode them separately, but then we get all the embeddings for all of the different images and all of the different attributes, and then we take an average of all of those vectors. And then that is the embedding of the item. So now on the query side, if you type in sneakers with 3 stripes, that embedding matches the item embedding, and that's how it shows up over here.
Oh, I see. So then you have the average embedding using the image and text. So you cannot really pinpoint if it is coming from one or the other, right? That's what you're saying?
Yeah. It's from an average, exactly.
Oh, I see. Okay, thank you.
I have a question because I once was using Selfie, and I was using the German word for wool, which is in Deutsch Wolle, and Baumwolle, so cotton and wool, and they couldn't differentiate for a long time because I think they are as well using the tags. I was asking if you having similar problems, or did you have the problem or not?
Yeah, so
Or you just using the
multilinguality.
English version? Okay.
Yeah, multilinguality is a problem that we had to fix. We fixed it by adding synthetic data sets so if you take articles, you can generate queries with it, in queries from it, both in classical ways and in these newfangled LLM ways, in different languages. So we have translations for all of the attributes of our products in whatever languages that we need, in all the markets that we are. So using that as training data helped the multilinguality part of it. But there's still room to improve. And I think the way forward over there is to upsample some, or do stratified sampling per language so that the model is sort of on an even playing field.
I just have another, because I'm not using Zalando, but you're selling as well used stuff as well. Is there a different problem between new stuff and used stuff in this search?
I don't think I'm the right person to ask that question to.
Okay, so then let's give another round of applause to Samay. Thank you very much.
Thank you.